Welcome back, everybody. That's the first thing everybody's going to hear. Why do we graph by hand? Why, if we have the technology, if we have our calculators, why? I might actually pull up. Hello? Oh, they want to bring me in for an automated. It was an automated person. I didn't just employ someone. So why do we graph by hand? Why do we even need a calculator? If we have the technology, why don't we just use our calculators, right? Well, there are certain things that the calculator will lie to us about. Get a more advanced calculator. There are certain things that the calculator will lie to you about. There's certain things the calculator will mislead you to. Like, for example, will a calculator ever show you a hole in a graph? Yeah. Well, on the visual, like if you hit the graph button, will it ever actually show you an open circle? No. Right. If you look into the table and you see and you investigate it that way, yeah. But you wouldn't know that unless you had done something algebraic. You know, you wouldn't have known that there would be a hole unless you would have done something algebraic, unless you would have worked it out. And there are other things like that. I know my calculator, for certain values, for certain things that I graph on my calculator, it connects top point to bottom point when there should be a vertical asymptote between there. Because all your calculator is doing is it just does a really good job of running numbers. It just does a really good job of calculating values really quickly and then connects the points in between them. So, I like to say that calculators are really, really smart, dumb objects because they do very, very basic things. They just do them very well, and they do them very fast. So that's all your calculator is really doing when it sketches a curve. It's just running values really quickly. It's not really like kind of analyzing what's happening in the graph and using that. It's just really running values. So that's kind of like the need of why we need to understand the different bits and pieces of the function, and so that we can tell what makes what happen in terms of the graph. So all we're going to do is just summarize everything that we know way back to like algebra 1, algebra 2. What do we know about how we graph a function? These are the things that we know. Well, the first thing that we can do is talk about the domain, right? The first thing that we do is talk about the domain. And I would write these down because you're going to be asked to, like the homework problems say, use the methods in the notes or something like that, or use the strategies in the notes. I forget the actual wording, but it basically wants you to run through A, B, C, D, E, F, G, H. I want you to do all of it. It wants you to show that and then graph the function. Okay. First thing, the domain. It's often very useful to start by determining what the domain of the function is. Where is it undefined? Is it only defined in certain places? Because that can kind of inform, if you have to do something with the derivative, that'll tell you, oh, well, I only need to worry about it between here and here because that's the only place that it's defined, or so on. Okay, it's often useful to start by determining the domain of D, the domain D of F. That is the set of values of X, which F of X is defined. We've been doing that since algebra 1. Same thing here with intercepts. I mean, we've been, maybe going back to algebra 2, we did a lot of, the most important pieces of a function are the intercepts. I said that a lot in algebra 2. Maybe not anymore. Maybe we might call them, they're not as more important than like a maximum or minimum value, but they're still a very important piece of information. The Y-intercept, but also the X-intercept. Remember, to tell the Y-intercept, you just plug 0 in for X and see what happens with your Y value. To find the X-intercept, you set Y equals 0 and you solve for X. Okay? I love they give this little thing here. You can omit this step if the equation is really difficult to solve. It's like, oh, okay, thanks. It just lets you just pass that, so like a free pass there. Okay. We don't do that. It's too difficult to solve. Right. Just a little there. Just very difficult then. Symmetry. Now, symmetry is one of those things that I don't think is too important because, it doesn't. If it's even, then obviously it's going to reflect over the axis. And if it's odd, like I like to tell, okay, if it's even, that tells me a lot. But if it's odd, I mean, I'm not going to go try to rotate it 180 degrees. I'm not going to try to do that. So if it's even, that's a really important piece of information. Now, how do you tell if it's even? Remember, if it's even, f of negative x is going to be equal to f of x, right? If you plug in the positive or the negative, it's going to come out to be the same thing. Why is that so important? Because that really kind of reduces our work in half. Okay? That reduces our work by a factor, by a factor of 2, because we can just reflect everything over the axis. Okay? If f is an even function and the curve is symmetric about the y-axis, that means that our work is cut in half. If we know what the curve looks like for anything to the right of the axis, of the x-axis, the y-axis, excuse me, then we can just reflect it over to complete it. For example, y equals x squared, y equals x to the fourth, the absolute value of x, cosine x, those are all even functions. Now, for odd, again, odd you can't really use too much in terms of graphing it, but I guess it's good to tell. That's whether it's odd. If you put negative x in, you get negative f of x, right? If you needed to, I guess, we can obtain the complete curve if we know what it looks like for greater than 0. All we have to do is rotate everything 180 degrees. Yeah, that's easier said than done sometimes. Simple functions like y equals x to the third, y equals x to the fifth, y equals sine x, those are all odd functions. Now, what's going to be really important when we talk about trigonometric functions is if it's periodic, okay? If f of x plus p is equal to f of x for all x and d, like what I'm thinking about is like sine function. If you have f of x plus 2 pi, isn't that the same as f of x? If you just increase everything by 2 pi, doesn't that repeat the same values over and over again? And factors of 2 pi as well, right? That's the same type, that's what I'm talking about here with the periodic function. Same thing with cosine x. If I increase it by a value of 2 pi, so we're saying like f of x plus 2 pi is the same thing as f of x because it comes up with the same y value. So therefore, I know that it's going to be periodic. I know that there's going to be a period to it, which makes our life a lot easier because if I can just take that chunk of the period, I will know that I can just repeat that and repeat that and repeat that to create my graph, right? I know that pattern will continue. So that really helps us when we create our graph. They give this funky one here. I think that kind of looks cool. I don't even know what that is. They don't even tell us what that is. I don't know. But those are all, this is another example of a periodic function. Okay. The next thing we're going to talk about is is asymptotes, right? Is asymptotes. To find horizontal asymptotes, remember that horizontal asymptotes, you kind of have to look at what happens on the far right side and the far left side, right? As x approaches infinity or as x approaches negative infinity of that function. If the limit as x approaches infinity of f of x is equal to a number L, or negative infinity is equal to L, then the line y equals L is a horizontal asymptote. So say the limit as x approaches infinity of f of x is equal to 2. Then, on the right side, it's going to flatten out to 2, right? Same thing going to negative infinity, right? If you know that there's either, as x approaches infinity, positively or negatively, if it goes to one number, then it will go to that value. That's a horizontal asymptote, okay? It says we don't have, oh yeah, it is still useful information. It says that as the limit as x approaches infinity of f of x, if that turns out to be positive or negative infinity, that's just really kind of determining our end behavior, right? That's saying on the far right side, positive even, that's my polynomial one, but you just basically have to look at as x approaches infinity of f of x, if it goes to positive or negative infinity, that's also pretty useful because then we know it continues up all the time or continues down all the time or on the left and right side. Vertical asymptotes, I do have to write something in here. They kind of present it in a kind of convoluted way. I like to say this: the limit as x goes to a either positively or negatively. So as I approach a number with the x values, okay, as I approach a number either from the right side or the left side of f of x, that has to go to either positive or negative infinity. Okay. and realize that I'm saying kind of 4 statements in one there with those pluses or minus signs. They show all 4 statements, but I think we can kind of figure out what those mean. You know, the limit as x approaches positive a, you know, not positive, but a from the right side, a positive of f of x. If that goes to either positive or negative infinity, then there's a vertical asymptote there. Same thing coming from the left side. If it either goes to positive or negative infinity at some point, some x value, that must mean that there would be a vertical asymptote on that. Okay. So horizontal asymptotes are, you look for what's happening as x approaches infinity. Vertical asymptotes, you got to look for as x approaches a certain value. Is something happening there? Is it going to positive or negative infinity? And we know those vertical asymptotes usually come up at, you know, if it's a rational function, you're looking where the denominator equals 0, right? If it doesn't cancel out top to bottom, well, that must mean that there must be a vertical asymptote at some point in there. Okay. Now, that is all kind of like review from Algebra 1, Algebra 2, right? We didn't get into limits and everything, but we talked about horizontal and vertical asymptotes pretty much all throughout Algebra 1, Algebra 2, and part of calculus. Now we get into the stuff that we learned this year, okay? The increasing decreasing test. Remember, for the increasing decreasing test, and this was an issue on the test, you have to find the derivative first. So a lot of people, some people trying to find the critical points didn't find the derivative first. You've got to find the derivative first, and then use your critical points for your increasing decreasing test. You compute f prime of x and find the intervals on which f prime of x is positive, which means it's increasing, or when f prime is negative, which means it's decreasing. That's that sign analysis where we did that number line, and we put our critical points on that number line and see where it's positive, negative, positive, whatever. And that tells you whether the function is increasing or decreasing. And again, remember that you plug your critical points, you plug the things around your critical points back into f prime. You don't go back into the original, but you go back into f prime. Then you use that increasing decreasing test to inform about your maximum and minimum values. Right? Your maximum and minimum values are where, you know, it changes from increasing to decreasing from your increase decrease test. You find the critical values of f, the number of the numbers c where f prime equals c, f prime of c equals 0, or where f prime does not exist. Then use the first derivative test, which is basically the same as your ID test, like your increasing decreasing test. If it changes from positive to negative, then it's a maximum. If it changes from negative to positive, that means it's a minimum. Although it is usually preferable to use the first derivative test, you can also use your second derivative test to kind of verify your results. Remember, if f double prime of c is equal to a positive number, then it's concave up, which means it's the minimum point. If f double prime of c is equal to a negative number, then it's concave down, which means it's a local maximum. And if f double prime of c is equal to 0, then you know there could be an inflection point at that value. Okay. And which leads us to concavity, right? Still haven't decided if it's concavity or concavity. And points of inflection. You compute f double prime of x and basically find the critical points of that, right? Where f double prime, oh, sorry. Well then, okay. We're gonna chip that. You're going to bed, right? Yeah. Oh, no. All right. Okay, so remember, you compute f double prime, and you basically find your critical points of f double prime. That's going to tell you where the possible inflection points are, whether it's concave up or concave down, and you do the sign analysis. And at that point, you use all of that information to sketch your curve. You use all of that to sketch your curve. So that's what we're going to do. Oh, wait, hold on. You can start writing down this one. That's what we're going to do first. Wait, right up. Yeah, maybe it says use the guidelines. I bet that's the wording in the homework. Use the guidelines. What that's basically saying is use the things that you know. There's A, B, C, D, E, F, G. Graphic. All right. Let's first start off by talking about the domain. Okay. What's the domain of this? Good. Everything but plus or minus 1, right? Set of all numbers x. I'll do it in set builder notation because it's easy to write it that way. Except for plus or minus 1. Now, how do we know that? Well, because the denominator, really the only tricky part about this domain is that the denominator can't equal 0. So if you set x squared minus 1 equal to 0, you get plus or minus 1. So it's everything but 1, right? A little bit easier just to write it like that. You could use interval notation, negative infinity to negative 1, negative 1 to 1, 1 to infinity, but a little bit easier to write it like that. Okay, part B says find the intercepts, right? Find the intercepts. Well,
talk to him. Let him know. Good job.
Kids these days. All right, so you're going to want to find where the numerator equals 0, right? So because that will be the zeros of the function, right? 2x squared equals 0, so x equals 0. Those are where the intercepts are going to be, so it's really 1 intercept. Crosses at 0. And also, if I want to find f of 0, right, the y-intercept, well, that's 2 times 0 squared minus 0 minus 1. 0, right? So my x and y-intercepts are both at 0, comma 0. Which makes sense. And that's what I kind of verified from the beginning, from that x-intercept. That's pointing 2x squared equal to 0. So it crosses through the origin point. Or at least it bends, or it bounces off, or it bends through it. We know at least the 0 is at 0, 0. All right, so now let's test to see, I always like to see, is it even? If I plug in f of negative x, what's going to happen here? Well, I would have 2 times negative x squared is equal to negative x squared minus 1. What's going to happen with those negatives that I just plugged in? They're going to go bye-bye, right? They're going to become positive. So it's going to be a 2x squared is equal to x squared minus 1. So f of negative x equals f of x. Okay, cool. So this is even. This is even. So in the end, I should see that this is symmetric about the y-axis. Okay, well, where is my horizontal asymptote? This is a rational function. So I can use things that we learned back before in algebra 2. Where is my horizontal asymptote? Not 0. It's at 2. How do we know that? Because the degrees are the same, right? This is neither top heavy nor bottom heavy. So therefore, I take the leading coefficient off the top or the leading coefficient of the bottom. So this horizontal asymptote is at 2. My horizontal asymptote is at y equals 2. We could verify that by taking the limit, and I did that on my page, but I'm realizing why would I do that? I know the rules for a rational function. Y equals 2. Okay, is there a vertical asymptote? Where would the vertical asymptotes be? Where the denominator equals 0, right? So let's see. Let's see if they exist. X squared minus 1 equals 0. So x squared is equal to 1. So x is equal to plus or minus 1. So therefore and does anything cancel out top to bottom? No. So these are not holes. See, if things canceled out top to bottom, they would be holes. If they don't cancel out, that's when I would have vertical asymptotes. Okay, and I can verify that using my limits if I wanted to, but I don't need to. Vertical asymptotes at x equals 1, x equals -1. All right, so let's continue on. Part E says to find, oh, we got to start doing our calculus piece now. We do the derivative. We're going to find the derivative of f of x. Now, f of x was 2x squared over x squared minus 1, right? So if I want to find f prime, I've got to use the quotient rule, right? The quotient rule. So that means I find f prime g, so 4x times x squared minus 1 minus g prime f, 2x times 2x squared, all over the denominator squared, x squared minus 1 squared. Everybody follow me there? I just applied the quotient rule to my original. It's the derivative of f prime g minus g prime f over g squared. And now let's reduce a little bit. So that means we factor anything out at all? I always try to check right here if we can factor anything out, because then we might be able to potentially cancel things. But it doesn't look like, I mean, I've got a 2x. I could do that. I don't know if that's going to help me, though. Let's just distribute in. Yeah, I've got 4x to the third minus 4x minus, 4x to the third. Oh, cool. Well, that's nice. I don't know why I'm saying that like I'm surprised. I've done it. Why is that nice? Because those are going to cancel out, right? So -4x over x squared minus 1 squared. So that's our derivative. So to find the critical points, I find where the derivative is either undefined or equals 0. And I have a potential of the derivative being undefined, right? I have a denominator. So I know that, I could say -4x equals 0. So x equals 0. And then this whole x squared minus 1 equals 0 again, right? Because x squared minus 1 squared, those are just the two factors of that denominator. So I potentially have x is equal to plus or minus 1 again. So we run our increase-decrease test at -1, 0, and +1. I'm going to cheat a little bit because I've already done this problem. This is positive, positive, negative, negative. We all know how we get that, right? We plug those values, something in between there, into f prime to see whether it turns out positive or negative. Right? So we would run them back through -4x over x squared minus 1. Honestly, isn't the denominator always going to be positive because it's squared? So really, it's all depending upon -4x. So anything below 0 would have turned it back positive. Anything above 0 would have kept it negative. That was a pretty easy one to do, though. All right, so what does that mean? That means for my increasing, I'm increasing on an interval from -infinity to 0, and then I am decreasing on the interval from 0 to infinity. I know there are asymptotes in there. I know. Like the book makes a really big point to point out that there are asymptotes at -1 and +1. So we would say that it's increasing from -infinity to 1 and then still increasing from 1 to 0, but it's technically not defined at 1 or -1. But at any rate here, I know that there is okay, what is it? Is it maximum or minimum at 0? It's increasing and then it's decreasing. It's a maximum point. So it's a maximum at 0, we know this point, 0, 0. It's the intercept. So its max is the intercept, the origin point. All right, now I want to find my points of concavity. So I've got to find f double prime now. So I've got to use the quotient rule again, because my f prime is this -4x over x squared minus 1 squared. So that means f double prime of x is going to be, f prime g, -4 x squared minus 1 squared minus, okay, but I'm going to put a big parentheses. It's going to take us a minute. G prime f. G prime f. Let's start off by writing f, negative 4x, because that's an easy part. Now, I've got to take g prime, the derivative of the bottom. Now, this is a chain rule. There is a chain rule there because it's x squared minus 1 squared. So I apply the outer. It goes 2 times x squared minus 1 times 2x. That's the chain rule, right? I take the power off, put it in front, 2 times x squared, leave the inside, x squared minus 1, and then kick it down to the first power. That's what you see here. And then I take the derivative of the inside piece, which is just 2x. And that's why you see that 2x sitting out there on the end. Now this is all over x squared minus 1 to the 4th, because it's x squared minus 1 squared. Now, do you see something in both parts of my difference? You see how they share an x squared minus 1? This is where I said earlier, I look for things that I could possibly pull out. Do they have a common factor? And they do. They have a common factor here, and it's an x squared minus 1. So we're going to leave it with a negative 4 x squared minus 1. Now I'll just raise to the first power because I pulled one out. Minus, and then I haven't done anything to this parenthesis yet, negative 4x times 2 times, and that x squared minus 1 got removed, times 2x. Now this is all raised to the 4th power again, but look at what I can do. I can cancel one of those out. I can say, okay, this is going to cancel, and this is going to turn into a 3rd power instead. And now I reduce the inside of this parenthesis here. That would be a negative 4x squared plus 4, and then a positive, look at that, that's a 4 and a 16, x, all over x squared minus 1 raised to the 3rd power. So finishing it off, oh, sorry, that's a 16x squared up top. 12x squared plus 4 over x squared minus 1 to the 3rd power, and I really hope that's what I got. So that's f double prime. All of that just to see if there's going to be inflection points. I know. Okay, so are there inflection points? Could there possibly, well, what are the critical points of 12x squared plus 4? Well, you've got to say, okay, 12x squared plus 4 equals 0. So we've got x squared is equal to, that should have to be, oh, that's why. Okay, I was going to say that's negative. So what's going to happen here? It's not going to matter because it does not exist. It does not exist. But there are other places, right? There are other places where the critical points are of the for the denominator here. So x squared minus 1 equals 0. So x is equal to plus or minus 1. Because you find the critical points of f double prime. Run my concave up, concave down test. All right, this is going to be, let's cheat here, positive, negative, positive. So what does that mean? That means it's concave up from negative infinity to negative 1 and from 1 to infinity. And it's concave down from negative 1 to 1. All of that to graph this problem. So here we go. Oh, yeah, that's true. Inflection point. That's pretty easy though. Inflection point. Where is my inflection point? Where could they be? Plus or minus 1. But are there actually points at plus or minus 1? No. So are there any inflection points? No. There are no inflection points because the only possibilities of them being inflection points would be at -1 and +1, but we've already seen based on the domain of this does not exist at plus or minus 1. There are vertical asymptotes there. So let's graph those vertical asymptotes. You know, that's where I would honestly start. Let's kind of put in our boundaries. Here's 1, here's -1. Put in 2, just for simple reference. Okay, what do we know about everything to the left of 1? Well, it's to the left of -1. It's concave up, right? And we also know, I actually should have put this in too, isn't there a horizontal asymptote at 2? So I can say at 1, 2, there is a horizontal asymptote. Let's put that one there. So if it's horizontal asymptote at 2 and it's concave up, it's got to go here. And if this is symmetric because it's even, shouldn't this look like this? Okay, we know we have a 0 at 0, 0, right? That's where it crosses. But it's all, oh, isn't that the local maximum point as well? So we can then say, well, if that's the local max and it's at 0, it must be bouncing off at that point. And also it's concave downward everywhere between -1 and +1. So that must mean it looks like this. Well, wasn't that fun? That was fun.
So how many of those are homework?
Like a couple.
So it's not a huge homework, but it's full.
But here's the deal. Did we learn anything new? No. We didn't learn anything new. Well, we should have learned anything. But that's really everything that's in the homework, except for there's a couple questions at the end that talk about just finding the slant asymptotes. And I'll do that at the beginning of the class on Monday and show you how to do that. And then we'll just do another couple examples if we possibly can.
Cool.
Yeah. I'm gonna say on Tuesday night. So that means that, you know, you can go ahead and do some of the homework problems this weekend because all it is just graphing. So in my, you know, there are several graphing problems on there. Do 1 or 2 of them this weekend. Just get it done with. Good? And then we'll do the rest of the in-class problems. I want to do one of each one and then do the slant asymptote. Oh, video.